Okay. Right, I continue. Any questions so far? Now, as we have looked at the example with independent threads, but normally threads interact, and most interaction is done through shared memory. Those variables which you declare outside of any function, let's say above main function, so that's the shared memory that threads can access. So this memory will be allocated in the data segment of executable. Of course, threads can also use heap, but in this case they should have pointers that points to the same location on the heap when they allocate. It's like, for example, main thread can allocate something called malloc, calloc, whatever, and then give this using some global pointer, so the threads can see this pointer, can access heap. So synchronization mechanism in pthread comes in the form of locks and condition variables. First we have mutual exclusion lock, which are called mutics in terms of pthreads, and condition variables, which are opaque objects that represents a queue of process suspended to be notified. So they're waiting for some whatever condition to become true, and when condition becomes true, someone notifies them, and they wake and they might check condition again. So readers writers log that allows shared reading and exclusive writing of shared resources. CMR voice, which is an extension of POSIX pthread application programming interface. API stands for application programming interface, or library if you will, which is implemented actually on top of mutics and condition variables, and they come as an extension. Okay, let's look at mutics first. So mutics is an object of this type, pthread mutics t, that you declare, that can be used to protect critical section or shared variables, how you want to say. So they just behave like a lock, right? How they implement it, the pthread specification does not describe how it should be implemented, but typically they implement it as spin locks, load, test, and set, this way. Okay, here it says before be used must be initialized. Maybe we can cross it. For old versions it is, but now you don't need to call init. In some examples, it might include in my example, you will see init, but it's redundant. Of course, if you put it, nothing wrong. Right? Okay, thread can set get mutix attributes if needed, otherwise I don't think it will be needed. It will just default attributes. Also, should be destroyed when no longer needed. I don't say must be destroyed. So if you care about memory, you can destroy mutix, or to ensure that nobody is using it. So declaration like this, where you give some arbitrary name to variable of this type. So functions are quite obvious. Okay, init is deprecated, so I'm not talking about it. Destroy, I don't think so. Lock, it's quite clear, lock the lock. Right, so this call is blocking, potentially, because if lock is locked, so then calling thread will be like blocked here until lock is unlocked, and then mutix. When this function returns, it means that the thread has locked the lock successfully. It executes the critical section, and then if it behaves correctly, it should call unlock. Right? So there is also try lock, which is a non-blocking call. It returns either non-zero or zero, just to indicate whether try has succeeded or not. Okay? So in this way you can put it in conditional. If try lock, then do something else, otherwise go to critical section. Some kind of to hide this waiting time for lock to be available, to execute something during this time. Okay, unlock is quite clear that thread holding the lock should unlock it. And here is also notion of ownership. It's only thread that holds the lock is able to unlock it. Okay, okay, that comes a typical usage of it. So this is redundant, as I mentioned. So you just declare it, you can lock it, critical section unlock it, and then non-critical execution. Here comes another example, which is called counters. And these counters, they will be executing this counter function. You see that there is a critical section here because result is somewhat local pointer, even though that it allocates on heap. But each counter function, each thread that executes counter will have its own like result, right? And this result is supposed to be added to the global total over there. And this global total is protected with a lock. I call it lock, okay? Mutex lock. So therefore, this critical section here is very short. To add result to the global total should be executed with mutual exclusion by one thread at a time. So therefore, thread should lock the lock, add result to total, and then unlock it. Okay. So main thread is here. So it executes main function. So it allocates like for result. Maybe there is some, of course, inefficiency here, redundancy. That's just for sake of illustration. Again, we are checking if there are any command line parameter. So in this case, this is R2E, this ASCII to integer. We convert this, and by like it should be n number of threads. If it's happened that it's more than it might be either 0 by mistake or negative even. So then we should default it to number of threads, which is, do you see it? It's up there, 5 threads, default. It defaults to 5. This is also like way how you usually read command line parameters, convert them to integers, for example, to numeric. Okay, here's a for loop, n times. Main thread creates n threads in this array, and each thread is given counter function to execute. You see there are two moves here to indicate that there are no attributes, default attributes are taken, and we don't care what counter function returns. Sorry, we don't put argument to counter function. This counter over here will be executed in 5 threads, and each thread will be iterating 1 million times, computing some random numbers which were summed up together, and then this random will be added to total. So main thread has nothing to do. It waits for children to join one by one in this for loop, and it prints finally total. I have also this example over here. Counter, I think it's called. Yeah, this one. Okay, let's compile it. Count C and execute it. And that, well, there'll be 5 threads. They compute somewhat result because it's random numbers, and then they sum up together. You can just roughly say it's 50 million multiplied by 5. It will be this number. So otherwise we can, if just to be sure. By the way, when you do this, like with matrix or whatever, I would recommend you to nullify it or to make it unimatrix with all ones, just to check that it really computes correctly, not just random numbers. Okay, that's my favorite editor. No, I'm kidding. So you know this VI editor, maybe? For example, so these counters, they compute results as randoms, which are not more than 100, it's 99. So let's put 1 here. Just a second. And comment out this. So they will be adding once, okay, to initial 0. Okay, we compile it again, and we run it again. And here you see that each one adds 1 million once, so it sums up to 1 million. And then 5 times it should be 5 million here, which is global total. Right. So also might be really quick. We look through source code, and you might come with some questions later or now. Then just don't hesitate asking questions. So all these examples I put as source code on corresponding module in Canvas. You can find them on the lectures. Okay, that was mutex lock. Just very short critical section here. So in your matrix in homework 1, when you'll be doing your threads will be workers will be accessing global totals, this aggregates that you're computing, sum, max, means. So they should be protected with either separate locks. It's up to you, or you can protect all 3 with 1 lock, a single lock. Because maybe having 3 locks just to add something or compute max, maybe it's too short. 3 times to lock and 3 times unlock. Maybe 1 lock is enough. For short critical sections, even with multiple variables, you can use 1 lock if it's short. Okay, condition variables are used to implement condition synchronization. And condition variable is known as also Q variable. It's an object of this type, pthread.conc. And they represent queues of process which are blocked, waiting to be resumed, to be signaled. And typically process is holding lock before it calls wait, because it was checking some condition. And then when it calls wait on condition variable, so the lock will be released automatically, right? And when wait returns, that means that the process has been signaled, that something has happened, like condition might become true, and it also got log back. So wait returns, thread is resumed to holding the lock. So you declare with some arbitrary name a variable of this type, and then operations is wait, signal, broadcast. There's functions which are described here. Okay, init is somewhat redundant unless you want to change attributes for whatever reason. I don't know what reason could be. Destroy. But the most essential is wait on this condition variable releasing this lock. Okay. You need to indicate lock because this function doesn't know really this thread who is calling what lock does it have, right? Because you know that one thread might hold not just single lock, it might get several locks. Then you specify here wait for some condition which is protected by this lock. So the lock should be released that someone can go and change the condition. Right? Signal, specify which condition variable to signal. And broadcast is like signal to all. Typical usage, which is illustrated by this like pseudo somewhat application. Imagine that we need to implement something like this. You remember wait statement, like hypothetical that describes synchronization. You wait when x is equal 0, take some action. Okay? It's like conditional take action when x is 0. And that's an action here. So take action is this invocation, this one. So we assume that x, because it's shared variable, it might be changed by other threads, and also we are checking it. And take action might also access some shared variables. We use lock, m, and imagine that this lock protects x and also protects action. So therefore, imagine that some thread executes this action. What does it do? It grabs the lock, m, it checks whether x is 0 or not. If it's not 0, it should wait, because It can take only when x is 0. If non-zero, it calls wait on this condition variable, releasing this lock, which was taken here. So at this point of time, thread is suspended, right, and doesn't have a lock. So this one is another thread. So this thread, imagine that it decrements x. Of course, you write it, so you should ensure that it should signal at some point. So therefore, if x gets to 0, it calls signal to condition variables. This signal should come over here, right? This thread is resumed, but wait does not return because lock is not given yet. And then this thread calls unlock. Now wait will return, and to be sure that x is still 0, it should iterate once more, right, to check, because there might be some other thread might grab the lock before and change x to something else. Then it takes action according to semantic of this await, and then it should unlock the lock. That's typical usage. Now one can ask, okay, I played the scenario that this wait comes before signal. What if signal comes before wait? Okay. It may happen that this thread, it executes first and it makes x equals 0. It says if x equals 0, yes, so it calls signal to condition variable, but there is no waiter. You remember that in case of condition variable signal has no effect. It's not memorized, it's not remembered, just lost. Okay? But what is essential that x is equal 0, and we assume that nobody is going to change it, right? So therefore, when this action is executed, it locks the lock, it checks x, it sees, oh, it's 0. It takes an action and locks the lock. And of course, you as a programmer should ensure that there are no any race condition that x has been changed by someone. Then, of course, if x has been changed after this signal, which was lost, so in this case, this thread will be suspended because x is not 0 anymore. And we will be waiting for next time when it will be signaled. So here comes this matrix summation. First homework, the first example. By the way, there was a typo in slides. The very first line was missing. I put it in here. This code might be slightly different from the one which is posted in assignments, but differences are not essential. Maybe we can look at the one that you see in assignments, huh? Shall we? Okay, let me. So this one, right? So let's download it. Right. Okay, let's read source code. What shall we do? Okay, there are some constants. Maximum size, we assume that matrix should not be more than 10,000 by 10,000. Otherwise, we might even run out of memory. So number of workers, 10. I don't believe that you have 10 cores on your laptops, even as me, but 10. Okay, this mutex and cron, this main chain counter barrier, which is over here. You remember counter barrier that counts how many threads he has called barrier, and when it reaches number of threads, so it let them go. Okay? Threads, when they call barrier, they lock the lock that protects counter, counts itself that, okay, has arrived. If arrival is equal number of threads, number of arrivals should set to 0 because we are going to use it probably, this barrier. And then we broadcast to go to threads which are waiting here to be resumed. And thread, if it's not the last one, then it doesn't take this branch because it's not equal. It calls wait on go. That's how you read barrier. But it's like helping think, and in this assignment you're supposed not to use it, right? Barrier. Okay, this is just also helping function to estimate execution time. Here comes a global variables, by the way, it's quite important. Size of matrix, which defaults to 10,000. Strip size is size divided by number of workers, because each worker gets, okay, I call them stripe, how you prefer to call it, like block of this, number of rows. And if it may happen that size is not divisible by strip size. It's like if you have, for example, 10, size 10 by 10, and you have 3 workers. It means the last one should get 4 rows, right? 3, 3, and 4. Okay? So therefore should be careful when you do the mean decomposition by just dividing the number of workers. Should be careful how you divide. And that's a match. This sums array that each worker will compute partial sum and put in this array indexed by worker number. So each worker has a slot here. And do you remember that they might be fault sharing? Okay. And matrix, which is given max size by max size, that's already like allocated in a data segment, static variable, in static memory, sorry. And the max size is 10,000 by 10,000. It's quite big matrix. It's a placeholder for the matrix. So then there is a main function. And main function, which is supposed to be executed by the main thread, is like entry point to C program. Okay, here is a plane with attributes, okay? So, but that's redundant, as I said. Just for illustration that you initiate attributes, you set scope to be Pthread scope system. It means that each thread on the system level, but it's a bit cheating because it's default anyway, so you don't need to set it. I also initialize mutex and con, that this is like redundant, this thing, you don't need them. So here comes a parsing command line parameters. If it's more than 1, so the first parameter could be size of the matrix, right? So if it's given, otherwise it defaults to max size. That's the size of the matrix. Second parameter might be number of workers, and if it's not given, it defaults to max workers. I'm interpreting this code, and I believe that some of you might be not so confident and with C. Well, but that's an opportunity to practice on it, to do homework in C. Okay, strip size is computed size by number of workers, but I said that the strip size might be not exact. That's how we will divide it. Here I initialize all once just to check, otherwise numbers should be maybe random numbers up to 98, module 99, it says here. Matrix is size by size. So here it says if def debug, so if you compile this code with -d debug, it will compile this, is a so-called conditional compilation. If you don't say -d debug, this piece of code will not be compiled. It will not be included, right? If you want to print matrix, why I put it on the conditional? Because matrix can be very big. So if you are printing it every time, so you could imagine how much print it will take. So how you time what you are going to execute? Maybe you should include create also. Here we take start time by reading timer. And then in this for loop, we create number of workers, and each worker is given worker to execute, and also it takes a number, which is loop counter from 0. So each worker has a number from 0 up to number of workers -1. Okay. And this, after that, because main thread is not going to join children, we can put also detach children here, if you will. So it just exits. Main thread exits, but application doesn't exit. Why? Because there are active threads still running. Okay. By the way, I never mentioned when the entire application exits, when all threads are dead. So and then we have a worker function which is executed in worker threads. So each thread gets its ID, actually its number, from 0 to number of workers. And then it computes what the first row of the matrix it should work on based on strip size. And the last one depends. If it's the last worker, it should say it should take size minus 1, just to avoid this not precise division result, like 10 divided by 3, I say. And then what they do, they just, each worker, it computes partial sum, like this is local total, by the way, it's not global one, because it's declared inside worker. And this total is stored into sums array, indexed by myID, and then they wait here until they complete at the barrier. So when all workers have reached the barrier, so they pass, and worker number 0 is responsible to print, to do sum of sums and print result. Okay? Number 0. My ID is 0, I'm the one. And the others, they just leave. Okay? So one can question, do we really need barrier here? What do you think? So actually it's worker number 0, the one that should be sure that all workers have completed, including itself, right? So one way that number 0 might be joining those workers. Because join is like some kind of implicit barrier, if you will, pairwise, because between the one who is joins and the one who is completing. So how is it? Any questions? So shall we execute it? I think I have here the one which is I have just shown you. Matrix sum. Yeah, it looks like. Yeah, it computes all once. Okay, let's compile it. So just to say, it's those who have never seen this before. So GCC is compiler, right? Minus source says what name of executable is optional, right? You want to have, otherwise if you don't say minus source, that means executable will have default name a.out usually, right? And then what you want to compile, matrix MC. Okay, sometimes it doesn't really read end of file, probably file will not properly written. And then you run this matrix. So the first parameter is size of the matrix. Let's take 10. And the second number of threads, 4. So it doesn't print anything, you see, that it prints only global total, which is 10 by 10 is 100, all once. And the execution time is pretty short. If you take 2, you could expect that it should be shorter. Yeah, and it's a bit slightly shorter, you see that, right? So if you take one thread, okay, that's I can't read. Let's say 8. So that's how you build some kind of performance evaluation, right? But I believe that on this box I have 2 threads, 2 cores. By the way, I said this debug over there. So you say minus d debug, like this. So when this conditional compilation, you say if something is arbitrary. I just call it debug. Right? You can call it whatever, x, y, z. But then you need to say compiler, I want this code, which is if x, y, z, to be compiled. Then you say minus d x, y, z, without space, no? Just like I did. Okay, now it complains about printing, because I can tell you why, because probably this one is long, and it says d, maybe I should say LZ, long integer, okay? But these are warnings about printing. You remember I was saying that I changed integer to long, but I forgot to do that in print. And then you run it. So now you see the matrix printed, okay, all once. And furthermore, each worker prints that I have started, and you see that. Huh? What else I want to show you? Okay, let's just change it to random numbers. Where was it? Initialization is here. So instead of all ones, I put some random here. So now it's random number, and okay, compute sum, it's not max, but in your case when you'll be computing max, it probably should be 98 if you take modulo 99. Modulo 99 means random numbers which are not larger than 99. It's 98 should be max in your case. And min obviously should be 0, I believe, with high probability. Even though that if in my matrix you don't see any zeros, by the way. You see that? There are no zeros. So therefore it's not necessarily that you may get 0 as minimum. No zeros here. 97. I see. I don't see 98 either. Oh, no, there is one over here. Okay, let's just come back to what I have more slides here. So that was an illustration of matrix sum, and what is the lesson here is that threads do not really so much interacting. They're reading some shared variables like strip size, size of the matrix, number of workers, and they're writing the results in this array, right, which with private like slots for each thread. And that might create false sharing thing, as I mentioned, because each write will, of course, will miss in the cache, that's definitely. But they're not probably reading it, it's just writing once. So therefore, you may think that it's not really so important, maybe, right? And so therefore, like an exercise, I asked you to modify this code so that they're not using arrays, but use like global total that they need to put there. And this access to global total becomes critical section. Right? And also, in this case, you might not even need to use barrier, because whenever worker is ready, it will put to the global total and can leave just, right? It doesn't need to wait for others. That's why I said don't use barrier for your homework. Now, I mentioned that this first 3 lines should be like mandatory. Don't forget to include them, because otherwise your program might behave strangely. Because what it says here that you would like to define this reentrant thing with underscore. Underscore, it means that for compiler and linker, saying that from this library stdio, which is not written by you, but you're using it, right, for I/O, for example, to read command line parameters, to print. So you would like to use versions of these functions which are so-called thread safe. And thread safe functions or reentrant, it means that these functions can be used in parallel threads simultaneously, and these invocations are not interfering with each other. They do not like interact through these functions. Okay, they're like independent invocations, and this can be achieved either having really reentrant function that has multiple simultaneous interleaved invocations which are independent, or it may be like protected. It's hidden from you, but inside it's implemented like having one lock that if thread calls it, only one thread executes there. Okay? Even though that you don't see that. Okay? semaphores, I think I will not continue with semaphores. Let's take it when we will have a topic lectures, and I will return to this slide, semaphores. Okay. But what I want also to mention, which was discovered by people from Ericsson when I was giving them course, and that was specifically in California, in San Jose, this group. Where was it? Which is subtle thing, but it might be crucial, by the way. Worker main thread. Yeah, here. So this look, pthread create. According to API description of pthread create, even on my slides, pthread create returns integer, by the way. It's not void function. Okay? Like many pthread functions, they return some magic integer. What do they return? They return success or failure. Success is typically 1. Okay? Pthread success, something like this. Constant, it's 1, more than 0. And formally, you should really check that thread was created successfully. Why? Because if this pthread create really fails for some reason, okay, then it fails silently. So your program keeps executing. You ask to create, let's say, by mistake, 1,000 threads. And at some point of time, your operating system says, no, I'm running out of threads. So pthread create will be failing, but your program will not notice that because it's silent, okay? Because you're not checking pthread create. And then you might think, oh, I have 10,000 threads, but in fact you might have just few hundred. That's what typically is supported with operating system, few hundred threads within heavyweight, like 300, 400 threads. So therefore, formally we should say here, if pthread create successful, or maybe it's just another way around. If not successful, pthread create, right? Then maybe we should inform user and maybe exit or do something. Is it clear? It was coincidentally discovered by one person doing homework, doing exercises in at Ericsson. But actually, if one can read documentation, when you use some API, sometimes you should read documentation also. And suddenly discover something, things.
Yeah. And the examples he use checking.
Huh?
And in the pthread link you have, they check if the thread was created.
I see. Yeah. Right. I don't know what to say anymore. If you don't have questions, you're free to go. And see you, I don't know when, tomorrow. Next lecture. Stop. So there will be another tutorial next time about Java threads. But I expect that most of